Okay, last few things on our what you need to know list. Number 9 on the what you need to know list says understand the kinetic molecular theory. I have this as a topic here. I didn't actually write them down, so you guys can look them up, but I'm going to read it off to you guys. Basically, the kinetic molecular theory that deals with ideal gases basically says that the volume of gas particles is negligible. And I remember I started off chapter 5 information telling you that whenever we're talking about the volume of a gas, we consider that the actual particle size is negligible. And we just say that the volume of the gas is the volume of the container. Okay, so rule 1 or part of theory number 1, it says volume of gas particles is negligible. Number 2 says particles are in constant motion. Yeah, gases are moving all the time. Like all matter is moving. Solids are kind of vibrating in place. Liquids are moving a bit, but gases, they're moving everywhere. Okay. Number 3 says that there is no no inherent attractive or repulsive forces. Basically, what this is saying that your molecules of gas are far away from each other, that there's no ability for them to be attracted to each other or repel each other. Okay, so they're not close enough. So there's no inherent attractive or repulsive forces. That's part of the kinetic molecular theory. Um, Now, all of that sort of goes out the door or the window or whatever when you force molecules to behave not in an ideal state. When you cram them into a very, very small space, then there may be some attractions. But in an ideal gas, there's plenty of place for them to roam, so there's no attractions or repulsions. Okay, and then number 4 says the average kinetic energy of a collection of particles is proportional to the Kelvin temperature. So all that says is that as you increase the temperature, the kinetic energy increases. So which makes sense. The higher the temperature, the more the movement of the gas particles. Okay, the next thing on the what you need to know list says understand diffusion and effusion and molecular speed. I'm going to tell you guys you can look up molecular speed and root mean square on your own. I'm not going to be giving you any problems on the exam with root mean square, but you may find some on the homework. But you know, you can always look these things up. But you do need to know effusion and diffusion. All right, so I have this diffusion and effusion here. On the second thing, I thought I had the definition here, but apparently I don't. Here's the definition for diffusion. It's the transfer of a gas through space or another gas over time. So when something diffuses, a gas will move from one area to another through another gas, or just by time it will diffuse. Effusion is different than diffusion, and this is the transfer through basically a membrane or through a hole. When something will effuse through a hole or effuse through a membrane, that's different than just diffusing over time and through space and through another gas. So diffusion and effusion are both movement of a gas through something, okay, either through another gas or through a hole or through a membrane. Okay, why do we need to know this? Well, because there's a law called Graham's law that relates effusion and diffusion with how fast it can go. So basically, how fast a gas will go through a hole, effuse, or go diffuse through another gas is related to its molecular weight or its molar mass. The bigger the gas, the heavier the molar mass, makes sense, the slower it's going to go. The lighter it is, the faster it will go. Graham's law basically states, and I think I wrote this down, yep, the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass. So, inversely proportional. The bigger the molar mass, bigger the molar mass, the slower it's going to go. The smaller the molar mass, the faster it's going to go. All right. This is the actual thing here. Rate of effusion of gas A over rate of effusion of gas B is equal to the square root of the molar mass of B divided by the molar mass of A. So let's say we had a problem where we want to know how much faster hydrogen is going to go through a hole, effuse, or go through a membrane than methane. So how much faster would hydrogen effuse than methane? All right, so let's say that gas A is our hydrogen and gas B is our methane. So how do we figure that out? Square root of A would be down here because it's the inverse. You put the molar mass of hydrogen. Hydrogen is 1.01 times 2 is 2.02. So let's erase this stuff so we can actually do the problem. Square root of 2.02 grams per mole down here. And this is methane. Methane is carbons 12, hydrogens 1, so this is 16. Okay. All right. So we get our calculator. 16.0, this is grams per mole. This is grams per mole. 16.0 divided by 2, and then you take the square root of that, and you end up with 2.8. So what is that telling us? It's telling us that the hydrogen will effuse 2.8 times faster than the methane. Okay, so the methane is going to take a longer time, 2.8 times more time than the hydrogen to effuse. All right? So if, let's say, the hydrogen effuses in about 3 seconds, the methane will be almost 3 times more than that. So it'll be almost 9 seconds it'll take it to effuse. All right, so that's that. And then we've got our last one, which deals with the van der Waals equation and the concept of a non-ideal gas. So let me tell you one thing, and this is important, and a lot of people get this wrong on the exam, and I'm not really sure why, but the most ideal situation for a gas is if the temperature is high. You want the temperature to be high. If the temperature is high, gas molecules are moving everywhere. They have a lot of space, all right? High temperature, good ideal situation. Low pressure, high volume. This is basically the scenario for an ideal gas. Why is this important? Well, if you have a very big volume and very low pressure, that means your gas molecules are not all squished into a small space. And if they're squished into a small space, then their size begins to matter and their attractive forces begin to matter. So in an ideal world, for an ideal gas to behave really, truly ideally, you want the temperature to be high, the pressure to be low, and the volume to be high. Okay? Now, what if we're not in an ideal situation? Then we need to tweak the ideal gas law. You remember how the ideal gas law is PV equals nRT? Well, the van der Waals equation corrects for non-ideal behavior. Non-ideal sounds like non-ideal behavior sounds like the gas is naughty or something. All right, so what is the let me write this down. Van der Waals equation. Van der Waals equation. And like I said, it corrects for non-ideal gas behavior. You don't have to memorize the equation, but just put it in your notes. P plus n squared A over V squared. So notice what we did. We took the P portion of the PV equals nRT and tweaked it with this over here. And then we go V minus NB. Again, we took the V part, tweaked it this way, and then the rest is exactly the same, nRT. All right, what do you guys need to know? Well, we need to know what A stands for, and we need to know what B stands for. What is A? A corrects for interaction between gas particles. So the more attracted they are to each other, the bigger the A value. Okay, so you're going to see that polar gas molecules have a high A value. All right, nonpolar ones, lower A value. When is this of an issue? It's when you squish them into a really tiny space. So having a small volume is not ideal for a gas. And if you are in a small volume, then you have to correct for the A value. Where do we get this A value from? It's a table in your book. This table over here. It is table 5-7. It says van der Waals constants for some gases. So you have a whole bunch of A values and B values. So for example, an A value for hydrogen, which is or helium, pretty nonpolar, is less than 1. But you have an A value for ethanol gas with potential hydrogen bonding, that is like 12.56. So the more polar it is, the bigger the A value is going to be. Now, what does B stand for? The B value corrects for volume. Corrects for the volume occupied by the gas particle. Yeah. Okay, what does that mean? Didn't we just get through saying that we're going to ignore the size of the gas particle, that the volume of the gas particle is negligible? Yep, that is absolutely true in an ideal situation. But if you are in a non-ideal situation, when a gas is behaving non-ideally because the temperature is too low, the pressure is too high, the volume is too small, then you start to have to pay attention to the actual size of the particle, and that is corrected for using this B correction in this area here. So let's take a look at some B values in the book. Again, that same table with the A values. Some B values here. Now, think about this. The bigger the gas molecule, probably the bigger the B value, and that is actually true. Let me see here. For SO2, sulfur dioxide, it's much bigger than a little helium. Helium is 0.0238 and sulfur dioxide is 0.056. So it's double the amount of correction B value wise. The, ethanol gas I was telling you about earlier, that has a 0.087. So more than 4 times the B value correction. So A value corrects for attraction. B value corrects for size and volume. All right. Do you need to know how to solve this? Well, if I give you a question with the van der Waals equation, I'll give you the equation and all you'll have to, and I'll give you the A values and the B values, and you just plug everything in. But more than likely, I want you to just understand the concept more and understand why you would use this, and what the A is for and what the B is for, and when a gas would be behaving ideally and when it won't be in an ideal situation or misbehaving non-ideal. Okay, good. We are done with the gas chapter. The next chapter is thermochemistry.